The electronic structure of the atom. How do you express the configuration of electrons within the electron cloud of an atom? First, here are some key terms that you will need to be listening for throughout the lesson. Make sure you know what these terms are talking about. When it comes to arranging electrons in the electron cloud, there are a few basic guidelines that have been set forth. These include the aufbau principle, the Pauli Exclusion principle, and Hund's rule. Each of these guides us through filling the various orbitals within the atom's electron cloud. First, we have the aufbau principle, which dictates the order in which the electrons fill the various orbitals. Simply stated, the aufbau principle says that the electrons will arrange themselves so that they have the minimum amount of energy possible. This is one of those huge ideas in science. Objects most often seek their lowest energy, just like a rock rolling downhill. Electrons are no different. They are most stable at their lowest energy. For the electron, the energies of the orbitals in the electron cloud follow a defined pattern, as shown in the diagram on the right of the screen. This energy diagram shows that the lowest energy orbital in any atom is the 1s. This is where every atom starts filling their electron cloud. From there, we move up the diagram from sublevel to sublevel, filling each one until we find homes for the number of electrons that we have. Next, we have the Pauli Exclusion principle. It puts limitations on the number of electrons that can be located in a specific orbital. According to the principle, no two electrons can have the same 4 quantum numbers. What this means is that 2 electrons can occupy the same volume, aka orbital, but within the orbital they must spin in opposite directions. This limits the number of electrons within an orbital to 2. Once the orbitals have 2 electrons, they are considered to be full and cannot hold more electrons. The next electron must go to the next allowable orbital until everyone has a home. Finally, we have Hund's rule. Hund's rule applies to sublevels that have more than one orbital. Orbitals in the same sublevel are considered to be degenerate, of the same energy. According to Hund's rule, as the electrons fill degenerate orbitals, they will occupy each orbital singly first, with parallel spins. This shouldn't surprise anyone, since electrons have a negative charge, and therefore repel each other. Having them in different orbitals minimizes that repulsion by allowing them to get as far from each other as possible. In addition, the similar spin causes the electrons to have parallel magnetic fields, increasing the ability of the electrons to stay away from one another. Once all of the orbitals have a single electron, a second electron will be added to the first orbital spinning in the opposite direction, a la the Pauli Exclusion principle. This will continue until each of the orbitals has 2 electrons. The aufbau principle, the Pauli Exclusion principle, and the Hund's rule allow us to express the arrangement of the electrons in an atom. We can do this through the use of orbital diagrams and SPDF notation. Orbital diagrams are a more visual method, while the SPDF notation is a more shorthand version. Each serves a purpose and is important to chemists. Let's look at an example to see how each of them is done. We'll start with the simplest atom we have, hydrogen. As the aufbau principle states, we start with the lowest possible energy, the 1s sublevel. To draw the orbital diagram, we draw a single line to represent the 1s orbital and then write 1s under the line. Now, since hydrogen has only 1 electron, we draw a single arrow pointed upward on the line. Some may ask, does it have to point up? The answer is no, but by convention we start that way. If you draw it pointing down, it's not really wrong, it just will look weird to other chemists. There you have it, the orbital diagram for hydrogen. It shows us that we have 1 electron spinning upward in the 1s orbital. Now for the SPDF notation. It's actually very simple. First, we write the 1s to represent the sublevel, and then, since there's 1 electron in the sublevel, we place a superscript 1 in the upper right corner of the S. There we go, the SPDF notation for hydrogen. If we look at a slightly more complicated example, helium, we start off the same way with the 1s orbital. We place a single arrow on the line in the upward direction, just like with hydrogen. However, helium has 2 electrons. There is still room in the 1s orbital for a second electron. However, the second electron must spin in the opposite direction to satisfy the Pauli exclusion principle. To show this, we draw a second arrow next to the first, but pointed in the downward direction. There we go, the orbital diagram for helium. The SPDF notation once again is simple. There are 2 electrons in the 1s sublevel, so we write 1s2. Let's look at one more example, carbon. We start pretty much the same way and fill the 1s with 2 electrons, one spinning up and the other spinning down. After the 1s, the next sublevel in energy is the 2s. Since it is another s sublevel and only contains 1 orbital, we draw a single line with a 2s under it. Since we have a total of 6 electrons in the carbon atom, we fill this orbital as well and place 2 electrons in it, spinning in opposite directions. Now, there are still 2 electrons left to find homes for. The next set of orbitals is the 2p sublevel. Here, there are 3 degenerate orbitals for the electrons to choose from. We draw 3 lines labeled with a 2p under the center line to represent these orbitals. Now, since these orbitals all have the same energy, we have to apply Hund's rule. We place the first electron in the first orbital, spinning in the upward direction. In order to follow Hund's rule, the next electron has to go into the next orbital, and it has to spin in the same direction as the first 2p electron. There we go. We have placed all 6 electrons in their correct places with their correct spin. The SPDF notation is pretty simple here too. We have 2 electrons in the 1s, 2 in the 2s, and 2 in the 2p. So the notation is 1s2, 2s2, 2p2. There you have it. We could go over more examples, but it's pretty much just more of the same. The more electrons you have, the more sublevels you need, the more orbitals you need. Just remember, start with the lowest energy and work your way up. You can only have 2 electrons per orbital, and they have to spin in the opposite direction of one another. Finally, electrons don't pair up until they have to, and unpaired electrons in the same sublevel have to have the same spin. If you keep these things in mind, figuring out electron configurations is pretty easy. It becomes even easier once you understand how it all fits in with the periodic table of elements. But that's for a later discussion.